Hi everyone, I'm Yunling. In this talk, I'm going to introduce our regression fault localization work. This is a joint work of Nanyang Technology University, National University of Singapore, Western Michigan University, Singapore Management University, and Xi'an Jiaotong Universities. Regression bug is a bug introduced when programmers modify existing code. When we find the code does not work, there can be a huge number of changes made from the original working version. The challenge here is to locate the failure-inducing change. Here is the traditional problem settings for locating regression bug. We have a test case T, an original program version P, where T can pass, and a regression program version P prime, where T can fail. We're going to find a set of changes from the total changes from P to P prime, which can serve as the root cause of the regression bug. There has been a lot of regression localization work to find the failure-inducing change, including delta debuggings and a symbolic-based approach. However, only reporting failure-inducing change is still far from enough to help programmers to debug in a straightforward way. First, a regression can happen not only because the programmers write something incorrect, but miss some change. In this case, there is no such straightforward failure-inducing change. The programmers need to explore the code context themselves. Second, even the failure-inducing is there and reported correctly, the work is not done. Programmers still need to spend time to confirm the report and figure out the fix. In this work, we proposed a trace alignment-based approach, which compares the execution trace of the regression and the original trace. Our approach can not only have state-of-the-art accuracy to locate the failure-inducing change. Moreover, our approach can further explain questions like why a step happens, and why a step does not happen, and why a step reads a variable with incorrect value. The approach can be used in both an automated way and an interactive way. In the automated mode, the approach can report the failure-inducing change directly. In the interactive mode, our approach allows the users to track the defects back to the root cause in a visual way. Here is a screenshot of our tool, which is implemented as an Eclipse plugin. In our tool, we list the regression trace in the left and the original trace in the right. When user clicked one step in either trace, our tool can automatically locate its correspondence in the other trace. User can compare the aligned steps by their line of code and the read and written variable value. User can also provide feedback on the trace step to track the data and control dependency along the trace to gradually locate the root cause. Now let me introduce our approach. In our approach, we first record the execution trace of the original version and the regression version. Then we develop a trace alignment algorithm to align the two traces. In this work, we address the following two challenges in our algorithm. First, because of the loop iteration, some program instructions or line of code can be repetitively visited in the trace. We need to align those recurring steps in the trace. Second, we need to match traces with equivalent semantics. Here is an example. The line 3 and the line 4 changes quite a lot from the left version to the right version. Clearly, the static semantics has been changed significantly, as the line 3 and the line 4 in the right is a loop, but they are just the conditional statements in the left. However, suppose we run both programs with the same input of x equals to 0. In the first iteration of the for loop, the step S3 should match to the step S3 prime. even if their AST syntax is completely different. So should S4 and S4 prime. In our approach, we convert the trace in a tree and represent the execution trace tree generalizable enough to detect those equivalent trace semantics. By this means, we can have a precise trace matching result. Interested audience can check our paper for more details. After the trace is aligned, we apply alignment slicing and alignment mending for tracking the root cause in the trace. Essentially, we are asking why and why not questions in an automatic way. In the alignment slicing, we start with a step. If the step reads the variable with incorrect value, we will track its dynamic date dependency on the same trace. In the meantime, we further find its corresponding step on the other trace and perform dynamic date dependency along the other trace. Those sliced trace steps serve as the answer for the question why the step reads the variable with incorrect value and why its corresponding steps on the other trace reads the variable with correct value. In the alignment mending, we can locate the unexecuted code as the root cause. Here, we still start with a step on the regression trace. If this trace step cannot be aligned with any step on the original trace, it means that it should not happen. Therefore, we first perform dynamic control dependency analysis to locate why the step can happen on the same trace. In the meantime, we search on the other trace for the question why this corresponding step does not happen on the original trace. In this example, we will find that there is an additional return statement to change the control flow, and we will report it. As a result, we can keep performing alignment slicing and mending until we can stop. The step where the algorithm stops are usually the root cause. We conduct an experiment on 24 real-world regressions. We select delta debuggings, and after, which is a symbolic-based approach published in XC15 as a baseline. Our experiment shows that our approach can outperform the baseline approach in terms of reporting much less false positives. Moreover, compared to the total trace size, the average trace size is about 64.1K steps. The visited trace steps by our alignment slicing and mending algorithm is about 13.1 steps. The explanation size is much smaller than the total trace. In summary, in this work, we propose a trace alignment-based regression fault localization and explanation approach. It can track the causality and propagate the defects back to the root cause. The experiment shows that our approach can locate the regression fault with the state-of-the-art accuracy. Moreover, our tool is designed to be explorable and interactive, which provides more flexibility for users to use in practice. And this is all my talk, and I'm happy to have your question.